So, good morning. Welcome to today's colloquium. I'm pleased to present you Professor Paola Marigo from University of Padova. And today she will talk about calibrating the role of thermally pulsing AGB stars in galaxies. To give a little bit of her curriculum, she graduated, she did her PhD in Padova in 1998, and then she moved to Munich for her first postdoc in the Max Planck Institute for Astrophysics, where she collaborated with Professor Weiss. Then she back to Padova, where since 2005 she is a permanent researcher at the Department of Physics and Astronomy. And now she's a professor in charge of the courses of stellar evolution and theoretical astrophysics. So don't expect an exam at the end. And her main research interests are about stellar evolution, nucleosynthesis, stellar chemistry and opacity, stellar population synthesis. And since 2014, she coordinated the project StarK, as you can see there, funded by the European Research Council, focused on the latest evolutionary phases of low mass stars. So I leave the word to Paola.
Okay. No. Okay. So thank you very much, Salvatore, for this nice introduction. Good morning, everyone. So before starting our scientific discussion, let me just really thank for this kind invitation to this institute, the coordinator of the research here, and also the director, of course, of the institute. And I also would like to thank the warm welcoming that I received during these days, in particular by Antonio, Rebecca, and Eva. So today I'm going to speak about the last evolutionary stages of low and intermediate mass stars, and I will try to express the importance of this phase, not only in the stellar context, but with a much wider feedback on the extragalactic research. So apart from a general overview on this topic, I will also present recent and ongoing efforts about this topic. And so let me just introduce some of my main collaborators that are involved in the ERC StarK project. So this is a sequence of not all, but the main collaborators as a function of the age, let's say, from the youngest to the older, also from a scientific point of view. Also, we have PhD students, postdocs, but also we rely on the contribution from senior researchers in Italy, but also in other countries in Europe and also in the United States. So the outline of my presentation will be the following. So first of all, I will try to describe what I mean by TP-AGB star conundrum that affect galaxy models up to high redshift. And so in this context, it is of course of primary importance to accomplish a physically sound calibration of this phase as much as possible over, and this is very important, a wide coverage of age and metallicity. And we will see how we can do this, at least we hope. Then I will move to give you some basic elements, just to recall some basic elements of stellar evolution, focusing on the asymptotic gem branch phase. Very short, just to summarize the physical processes. And then I will move to describe two important elements of this research. One is based on theoretical grounds. So the idea is to develop a all-round theoretical approaches to couple all processes that are involved in this phase. And the second part, of course, deals with observations. Without observations, we will not be able to constrain this very important phase of evolution. So the theory from first principle nowadays is not able to do the work alone. So observations play a key role in this context. And So I will show you some efforts that we are developing along the calibration cycle, speaking about galaxies, nearby galaxies or clusters. And then, of course, I will close the talk giving some brief overview and pointing out future perspectives of this research. So this is a drawing that attempts to give you an idea of the complexity of the physical processes that characterize the asymptotic giant branch phase. This phase is characterized by a lot of nucleosynthesis, rich in nucleosynthesis and mixing events that will alter the surface chemical composition. Also, these stars are experiencing radial pulsations. Myra are one of the examples, of course. These stars also in the outer layers are characterized by a complex molecular chemistry that also determines the, let's say, the conditions for the subsequent condensation of dust and growth in the circumstellar envelopes. And actually, these circumstellar envelopes are being ejected into the ISM via strong stellar winds that characterize the phase. So you see, it's a very complicated picture that we have to try to describe with theory. And what it has emerged in the recent years is that all these physical processes contribute to produce identifiable features that are seen not only in the stellar spectra via prominent absorption molecular bands or dust features, but these processes affect also the spectrophotometric properties of galaxies when they are resolved in single stars. This is, for instance, the Spitzer-Sage near-infrared column magnitude diagram of towards the LMC, and these red and yellow stars represent really these AGB stars, so they are the most evolved that are also obscured by dust. And last but not least, AGB stars are found also to affect the observations and the interpretations of distant galaxies for which you cannot resolve the single sources and up to high redshift. So this is a case, for instance, of the interpretation of the spectral energy distribution in post-starburst galaxies. Okay, so the bottom line is that the TP-AGB phase is really crucial for a wide variety of interpretation of astrophysical context. But despite the far-reaching, I'm sorry, I have also this one that is very interesting, I think. This is a collection of 3 cases in which the TP-AGB stars' contributions can be possibly seen in integrated galaxy spectra. For instance, here we have a sample of a nuclear spectra of AGNs, and it has been detected clearly the CN absorption band at roughly 1.1 micron, and this of course may point to the existence of carbon stars, and so this could imply a possible recent star formation. Then also, if you, by an analysis of a Spitzer spectra of early type galaxies in Virgo, it was evident that there was a well-prominent emission at 10 micron that could be caused by silicates that form in the outflowing material from low mass oxygen-rich AGB stars. So also in this case, AGB stars can play a role. And this is another interesting case in which, again, in early type galaxies, they found the features of the PAH emission. And it is difficult to interpret the existence of PAH emissions maybe in elliptical galaxies. Maybe this points to the existence of intermediate age stellar population or maybe episodes of star formation, of recent star formation. despite the far-reaching importance of the TP-AGB phase, what turns out in the recent years is that there is actually a debate among the different modelers on the contributions that TP-AGB stars can provide to galaxies. Just to give you an example, this is a composite spectral energy distribution of 64 post-starbust galaxies. So they are the gray dots, the observations, and superimposed we have models, the lines, that corresponds to the predictions of two among the most popular stellar population synthesis models, namely Brusoil and Charlot and Maraston. And the lines are the best fitting models for these post-starbust galaxies. So what you can see is that there is a general convergence of the different models at shorter wavelengths, whereas they start to deviate significantly at longer wavelengths in the infrared domain, where the contribution of AGB stars become dominant. And so this means that the modeling of AGB, of the AGB phase inside the galaxy models is really critical, because usually this fitting of the spectral energy distribution is used to derive basic parameters of galaxies, like stellar masses and ages. So discrepancies in fitting the sets would, of course, produce different results for this galaxy parameters. And this is another example. So this is a sample of galaxies in the Hubble ultra deep field, and these are 7, I think, yes, galaxies that are fitted with some population synthesis models, the same galaxies can be fitted by different population synthesis tools, and here are the results in terms of masses and ages for the same objects. So you see here you have Brusoil and Charlot, Maraston, and this is also another release of Brusoil and Charlot models. So you can see by just comparing the height of the bars that actually you may expect a discrepancy by about a factors of 2 or 3 in the mass and ages determination, which is a lot. So that this may have an important implications for all the discussion about galaxy evolution. Just to conclude, I also consider interesting to put this plot that shows the is based on the cosmic star formation history derived from the Millennium cosmological simulation. Here you see the star formation rate, and the metallicity evolution as a function of the look-back time. And in the top panel, you have different colored curves that correspond to the percentage contributions made by TP-AGB stars to the K-band in the rest frame in these simulations. And so you see that the different curves, so the contribution can reach up to 40%, for instance, at these ages. By the way, the contribution shows some peaks just after the post-starbust phase. And so the different behaviors of the curves underlines a different treatment of the TP-AGB phase in terms of the mixing, in terms of the mass loss, and nucleosynthesis. So again, you see that the impact can be quite high. So we have really a propagation of the uncertainties in the stellar context concerning this phase into the galaxy framework in terms of mass to light ratios, galaxy masses, ages, and also star formation rate. So I hope I have convinced you that it is really crucial to make physically sound, to understand how these stars behave and what are the main physical processes and how they depend on mass, which means age and metallicity. So actually what we want to know is how the TP-AGB properties vary in this diagram. So as a function of the age and metallicity, this is just an example. For instance, it would be crucial to know what is the expected evolution of the C over O ratio that we will see plays a critical role in determining the evolution of these stars. I mean the photospheric C over rho ratio. Okay, so this map shows one possibility that is given by our models in this moment, and so it is, of course, the behavior is driven by the occurrence of mixing events like the third redshift or nucleosynthesis like hot bottom burning, but we will see it in more details next. So what are the basic quantities that we want to constrain, having in mind the main goal of calibration for TP-AGB stars? They are very simple, apparently. So the lifetimes, the duration of the phase, the luminosities, the abundances, of course, because we will see that AGB stars make a lot of a great contribution to the chemical enrichment of galaxies, and of course mass loss, how much they can lose and how fast. So lifetimes and luminosities in the context of galaxy evolutions are very important to be known, because the integral of the luminosity with time gives the energy output that is contributed during the phase, the so-called full. Right? So if we know the energy output, we can also know what is, for instance, the relative luminosity contribution that is provided by TP-AGB stars as a function of age, which is also very important. You see that in this plot, for instance, we expect a peak of energy contribution by TP-AGB stars at around roughly 1 giga-year, intermediate age populations. Of course, knowing the abundances and the mass loss coupled together lead to the knowledge of the chemical contribution by these stars in form of gas and dust. This is very important, and also in form of dark remnants like white dwarfs, final masses. And so without a calibration of these quantities, also the sets of chemical yields that you can use need to be tested. I mean, so the chemical yields can vary a lot depending on the lifetime and the efficiency of the mixing. Okay, so a few words about the basic features of the asymptotic gem branch phase. So just to recall you some stellar evolution concepts. So the AGB phase is common to all low and intermediate mass stars and starts right after the exhaustion of helium in the center. So in this HR diagram, the AGB phase is colored in light blue and in blue, and it is divided in the early AGB, that is a quiescent phase in which the helium burning shell provides most of the luminosity, and then this final phase is the most intriguing one, is called the thermally pulsing asymptotic gem branch phase, because it is characterized by the quasi-periodic occurrence of thermal instabilities of the helium burning shell that are called thermal pulses. So just note that we shouldn't confound the thermal pulses with the radial pulsation of these stars. They are completely different processes. So here we are speaking of thermal instabilities of the helium burning shell, but of course these stars experience a periodic variation due to pulsation, but they are different. So during this phase, AGB stars experience a unique nucleosynthesis, mainly determined by the third redshift that we will see in a moment, and also they experience a strong mass loss that eventually lead to the ejection of all the envelope into the ISM, and what remains is a bare central star that will finally evolve along the cooling sequence of white dwarfs made of carbon and oxygen mainly, whereas the ejected material may shine in recombination forbidden lines as planetary nebulae. Okay, so the typical structure of a TP-AGB stars consists of a very dense electronic degenerate carbon-oxygen core surrounded by two burning shells, the helium burning shell and the hydrogen burning shell. Then there is a very expanded tenuous convective envelope in which the abundances are homogenized, and outward there is also the action of strong stellar winds that form circumstellar envelopes that are now, of course, subject of many studies, also with the aid of ALMA, for instance. So it is interesting to notice that all the rich nucleosynthesis that AGB stars experience take place in this very narrow range in mass region. It's let's say, involving the helium, the intershell, and also part of the bottom of the convective envelope. So let me just summarize with few words what are the main physical processes that can determine the variation of the abundances at the surface of AGB stars. The first one is the third jump. It takes place in concomitance of thermal pulses when the envelope is able to penetrate inside where a previous pulse was developing. So what is this? This is a convective region that develops by the occurrence of thermal pulses, so that this region becomes convective. And in this region, a lot of nuclear reactions takes place during thermal pulses. Triple alpha reactions producing primary carbon, for instance, but also maybe some oxygen, and other alpha capture reactions producing neon-22, magnesium-26, plus, of course, the very important S-process neutron capture reactions that will lead to the synthesis of elements heavier than iron. Okay, so this takes place during thermal pulses in the pulse-driven convection zone that is depicted here, and soon after, when the envelope is able to penetrate, these new synthesized elements are brought up to the surface by the convective currents. Okay, and so there is an enrichment of different elements, and some of them are written here. Okay, so it's an important process that has a very short time scale of the order of 100 years or so. What is the most important effect of the third jump? Is the formation of carbon stars. So you expect a progressive enrichment in carbon, and so you can explain the existence, for instance, of S-type stars, where the C/ρ ratio is growing and it is approaching unity, still below 1. And then if the number of carbon atoms exceeds that of oxygen 1, then you have the formation of a carbon star that is characterized by a C/ρ ratio larger than unity. This is just an example of how you expect, this is just one model, the abundances change as a function of time for a star that is experiencing the third jump. So you see that the yellow line, that is the carbon-12, is progressively increasing, and at this point it overcomes the oxygen abundance, and we expect the formation of a carbon star. Okay. I have to speak about 2 words about the fact that, unfortunately, despite being so important, the third jump is uncertain from first principle, because still we lack a strong, robust theory of stellar convection and mixing. So the efficiency of this process, that is prescribed by this parameter lambda, the larger is lambda, the deeper is the envelope penetration, is very uncertain. And just to give you an example, here I plotted lambda as a function of the core mass for the same star with the same mass and metallicity, and these are the predictions by different stellar modelers, okay, different stellar evolution codes. So completely different, you may have predictions. This means completely different predictions for the chemical yields, for instance. Okay. And another uncertainty, and this is the focus of recent studies, is also the chemical composition of the intershell, so the chemical composition of the material that will be dredged up to the surface. So classical models predict 20% of carbon, 2% of oxygen, and the rest helium. But depending on the application or not of overshooting below the base of the intershell, you may expect a completely different chemical composition of the intershell with a non-negligible contribution in oxygen, for instance. This has attracted the interest of many studies in this period, and so also this part should be tested, and actually what we can do is try to calibrate these uncertainties, to reduce these uncertainties via observations. So abundances in AGB stars, planetary nebulae, and post-AGB stars would be of critical importance, and I know that here there are researchers that can contribute greatly to solve this issue about the third age up. Yes, so the second important process that affects the envelope abundance is hot bottom burning. While the third age up was taking place during the thermal pulses, hot bottom burning is taking place during the interpulse periods, so during the creation phases, and corresponds to the activation of hydrogen burning cycles when the base of the convective envelope reaches quite high temperatures of the order of several tens of million Kelvin degrees. Okay, so during this interpulse phase, you have, for instance, the activation of the CNO cycle. Other chains are also involved, like the neon, sodium, magnesium, aluminum cycles, and also you may have the production of lithium. So this process is expected to take place only in the more massive AGB stars. So you need to have more stars with masses larger than about 4, 5 solar masses to have this process at work. Of course, this depends on the metallicity, but these places, of course, speaking about initial mass means speaking about age. So you expect this process to be present at younger age, at around 10 to the 8 years, not older. And okay, I will not spend too many words here. It's just to show you the CNO cycle and the other chains that are involved. There is also the possibility that via a particular process called Cameron-Fowler beryllium transport mechanism, AGB stars can synthesize lithium-7 that is also seen in the spectra of the brightest AGB stars in the Magellanic Clouds, for instance. And this needs a particular coupling between convective timescales and nuclear timescales. But actually, we can model the production of lithium quite well. So this is another example of hot bottom burning nucleosynthesis calculations that I did recently with different isotopes involved. This is the temperature as a function of time. This is the C/O ratio, and these are the abundance evolutions. So what we expect is that hot bottom burning is more efficient at decreasing metallicity. The main effect is that converting carbon to nitrogen, hot bottom burning can prevent or delay the formation of carbon stars. So you expect most hot bottom burning stars being oxygen rich. But what is also interesting to notice is that if you go to very low metallicities, because also oxygen is destroyed in favor of nitrogen, you may expect an increase of the C/O ratio because of the destruction of oxygen. So maybe these will appear as bright carbon stars, very massive. And you expect also the enrichment in other interesting isotopes like sodium-23, aluminum-26, magnesium-25 that are receiving a lot of attention now, for instance, in the framework of the chemical anticorrelation seen in globular cluster stars. Okay, what is the status of this process? So I think that the qualitative picture of this process is okay. So I think we more or less understand, but again, the results can vary from author to author, for instance, depending on the adopted convective model, either the mixing length or the full spectrum of turbulence, also other parameters are involved. So again, I think that observation will play a key role here to calibrate the hot bottom burning process. Few words, so all these processes, third age up and hot bottom burning, affect the evolution of the C/O ratio at the surface. This ratio plays a critical role in the evolution because, first of all, it affects the equilibrium of molecular chemistry and dust formation. Just to give some basic physics concepts, the carbon monoxide molecule is the molecule with that is the most stable one among the known molecules. And so this means that depending on the C over O ratio, you may have a completely different chemical pattern. Okay, so if you are in presence of a C over O ratio lower than 1, it means that all carbon is locked to form the carbon, most of the carbon is locked into the CO molecule, whereas the excess of oxygen is involved in the formation of other oxygen-bearing molecules like titanium oxide, vanadium oxide, water, that are seen in the absorption molecular bands in the spectra of AGB stars. The reverse is true for a C over O ratio larger than 1. So in this case, it is the excess of carbon that forms the molecules like C2, CN, and so on. And actually, depending on the C over O ratio, you can explain the spectral dichotomy of AGB stars, both in the optical but also in the infrared where the dust operates. So this is just an example of two spectra in the optical. One is for an M star. It is dominated by titanium oxides band, and this is a carbon stars where the CN and C2 absorption features are present. And if you move to longer wavelengths in the near and mid-infrared, again, you see, for instance, for a C over O ratio lower than 1, a prominent emission of 10 micron due to silicates. So it's crucial to have a good modeling of the processes like third dredge-up and hot bottom burning, because these affect the C over O ratio, which in turn affects the observed spectroscopic and also photometric properties of these stars. 2 words about mass loss. This is also another fundamental process that affects the evolution of these stars. So this is the mass loss rate as a function of the period. These are observations taken from AGB stars in our galaxy. So you see that observations seem to indicate an increase of the mass loss rate with the period, and until some constant or nearly constant value is reached. And the models indicate that this kind of behavior can be accounted from some kind of pulsation-assisted dust-driven winds. So pulsation will make a matter levitate up to regions where the density and the temperature are suitable for dust formation, and then the momentum absorption by dust can trigger the mass loss. Okay, but before you see, before this this very prominent increase of the mass loss, you still have non-negligible stellar winds, and this is what I call pre-dust mass loss, just to have an idea. And there are studies that are indicating that these mass loss that should be present before the dust is making the stellar winds could be associated to cool chromospheres, to the presence of alpha waves. Again, here we have to try to describe as more accurate as possible the mass loss, because this is a primer process. So the situation is not very good in the sense that there are a lot of efforts, also very good efforts, but the scenario is still not definitive. So for the pre-dust mass loss, we don't have many theoretical details. We still have to rely on empirical calibrations, going back to Reimers, and but then also more recent efforts by Schroeder and Kunz. For carbon star dusty models, the situation seems more or less okay. So the mechanism seems to be understood. It's not the same for oxygen-rich stars, and there is a very big issue here. What is driving the mass loss in oxygen-rich stars? So apparently, absorption by dirty silicates is not doing the right work, and there are now recent suggestions that maybe you need to consider scattering from large grains to drive a wind. So there is a lot of very good work going on, but still we cannot use these results into stellar population synthesis. And the dependence on stellar parameters is still to be known. Okay. I have to speed up, I think, a little bit. So, yes. So, there are three classical methods to include the AGB stars in galaxy models. I just listed them here. So, in principle, the most accurate is the use of full stellar models, of course. All the physics, apparently, is there. But, of course, there are some numerical issues sometimes coming out, and also they are computationally intensive, because for a calibration, as we will see, we have to compute many and many tracks, thousands of stellar evolution tracks. Then you can rely on synthetic stellar models, which are completely analytical. So they use fitting relations derived from full models. So the drawback here is that they are very fast. They are suitable for statistical analysis, but they lack a lot of physics. So this is also a very important shortcoming. There is also another possibility to use integrated models. These essentially are the models developed by Marastone, in which essentially the resolution, the single resolution element is not one star, but it is a simple stellar population. Okay, so it's something already integrated with an IMF, and you are only dealing with integrated fluxes. So there is no stellar evolution modeling inside these models, because they are empirically calibrated on Magellanic Cloud clusters in terms of integrated luminosities as a function of the age. So each of these treatments has advantages and disadvantages. So we try to optimize the use of stellar models inside the StarCrib project that is designed around a multidisciplinary approach, in which we try to couple, from a theoretical point of view, all physical processes together, also to probe the reciprocal feedback. Okay, starting from stellar models, stellar spectra, wind models, dust growth models, and pulsation models, and to put them to operate together. So it's a very challenging task. We are working on this. So a few words about the theoretical tools that we are developing. So the TP-AGB evolution is followed with the Colibri code that optimizes the ratio physical accuracies versus computational issues. So a unique feature of this code is that we can rely on the fly computation of molecular chemistry and opacities without any interpolation. So we can follow the changes of the chemical composition. A nuclear network is included, coupled to a diffusive description of convection to follow hot bottom burning. We have a parameterized description of third ridge up, because we want to calibrate it, and mass loss. Okay, this Colibri code is particularly suitable for the calibration because it is physically accurate enough, but is also quite quick to make a lot of computations. So we can rely on a very accurate model atmosphere. So this is a schematic plot sketch, let's say, of the photosphere and the circumstellar envelope of AGB stars. So I'm focusing now on the atmospheric layers, and in Colibri we have the possibility to follow, as I told you, the evolution of 800 species, molecules and ions as a function of time with no interpolation, and also to compute the opacities. This is just comparing opacities with a C over O ratio below 1 and above 1. You see that they can vary a lot. Please note the dynamical time scale, sorry, the dynamical scale here is very large, order of magnitudes. Okay, by the way, for anyone interested, there is also a dedicated web interface in which you can retrieve tables of Russell and mean opacities for whatever chemical composition you want. So, in this code, we can link the nucleosynthesis. Again, these are abundances as a function of time for a star experiencing hot bottom burning in the third ridge up, with the molecular chemistry. So as a function of time, the bottom panels show the evolution of the abundances of different molecules, some of them. in the photospheres of this model. So you see water, vanadium oxide, and CN, silicon carbide, and so on. Okay, this is done for every track, every time it is calculated. So in principle, we have a wealth of information. Grids of cool stellar spectra are also computed, and Bernard Halligan is taking care of this. He's computing large grids of cool stellar spectra as a function of different stellar parameters, including the C over O ratio, and these are also available in the web pages and interfaces we developed. We tried also to move outward into the circumstellar envelope, so giving some description of this region that is close to the photosphere up to few stellar radii, in which shocks are expected to take place due to pulsation and stellar wind. And so, okay, without entering into many details, a shock formalism has been adopted, and it has been tailored to the Colibri code on the basis of the Church-Neff formalism. Okay, so in this case, we moved from equilibrium chemistry that is computed with the Opus code. This is just an example, into non-equilibrium chemistry. So we have a network of reactions that are solved, and you can see how different can be the non-equilibrium and equilibrium chemistry for the same atomic abundances. Okay. And then we go to the description of dust formation in AGB circumstellar envelopes in this light region here, which is very important also for the driving of the wind. And in this case, Ambranani is taking care of the calculation of the dust growth by solving the equations that regulate the growth and the destruction of the grains. Okay, so this is done for different species, including silicates or amorphous carbon, also silicon carbide, and these models are calibrated, let's say, in order with some parameter, for instance, the sticking coefficients or other processes like the chemi-sputtering, to reproduce the observed data of Vx, so the expansion velocity as a function of the mass loss rate. Okay, and the important point that, again, these dust growth models are tailored to the Colibri tracks, so to the TP-AGB tracks, as a function of the stellar parameters. That is what we want. So what we can produce is the prediction of AGB dust yields. Okay, for instance, olivine pyroxide and periclase amorphous carbon as a function of time, also dust to gas ratios, and the dust yields as a function of the initial mass and metallicity are also available. Not only, the dust yields are important, but also the impact of the dust on the spectrophotometric properties of AGB stars. So we are using the dusty code to compute the radiative transfer calculations for the dust reprocessing. And just to give you an example, this point should be the non-dusty, the dust-free point in this color magnitude diagram, and the different lines corresponds to different radiative transfer calculations made with these stellar parameters. With the aid of Dusty, Ambranani did these calculations and increase in mass loss rate. Okay, so again, the radiative transfer calculations are tailored to the stellar evolution tracks. So in the end, we can construct large grids with all this information of stellar tracks having also the dust incorporated for 70 values in this moment of large values of metallicities. We need to have a good resolution, at least a 70 value of the initial mass for each metallicity, for a total of roughly 1,500 TP-AGB tracks calculated for each combination of parameters. So if I want to change a parameter for the threaded job, I have to recalculate everything. That's why we need something that is also quite agile and to have a quick testing. So the gain factor compared to full stellar model is a factor of 100, more or less. So the natural product out of these tracks is to compute stellar isochrones for stellar population synthesis. And recently, a lot of effort has been put in collecting all these studies together and to put a lot of information in these isochrones, including the effects of the pulse cycle variations that can be very important when studying AGB stars, and also the chemical composition. So this is an example of a few isochrones for a few selected values of the ages that are, for instance, characteristic of massive M stars with hot bottom burning, 100 million years. This is the domain of carbon stars, few gigayears of age, and this for 10 gigayears is the domain more or less of low mass oxygen-rich stars. Okay. Okay, we have the possibility of having a large database of photometric systems that are available for all the measure surveys, and they are convolved with filters to produce large tables of bolometric corrections as a function of log G, effective temperature, and metallicity that are being interpolated in the isochrones. So any filter system can be included in less than 1 hour. This is just to show the effect of introducing the dust reprocessing in the circumstellar envelope. So this is observation, this is a simulation, and this is a simulation with the dust. So you see how much critical is the effect of the dust. And many filters have been included. So I have 5 minutes. More or less. Yes. Less? No, okay. So I have to hurry up a little. So population synthesis is made in our group with a trilegal code that couples a lot of efforts. So starting from evolutionary tracks and isochrones, we have to link the population synthesis with the stellar spectral libraries, pulsation models that are ongoing, circumstellar dust, and then for a given set of input parameters like the star formation history, age, metallicity relation, distance, and so on, it is possible to produce a catalog, a synthetic catalog of stars, and so that you can compare observations with simulation in terms of star counts, luminosity function, color distribution, period distribution, and so on. Okay, so how to calibrate the AGB phase now with population synthesis once we have all these tracks and isochrones and so on. The classical calibrators have been so far considered the Magellanic Cloud clusters. So you can calibrate your models as a function of the age or as a function of the turn-off masses for these clusters to provide information about the integrated AGB contributions like in Marastone, or directly from star counts you can derive constraints on the lifetimes, or you can also use these clusters to calibrate the infrared colors as a function of the age. Okay. I have no time to discuss here this particular effect, but we recently showed that the peak of the AGB contribution that is expected at around 1.6 gigayear could be really overestimated in earlier studies because of an evolutionary effect that is related to the non-monotonic behavior of the lifetime as a function of the mass. So without entering into many details, what you can show here, here you have an age versus initial mass. In red, so you see that there is some non-monotonic, some change here in the behavior, and you see that at this age, so this would represent an isochrones, for instance, the TP-AGB phase, that is the red line, is encountered 3 times at least in this case. So this means that you expect an abrupt increase of the TP-AGB contribution, that is, for instance, a boosting of the AGB phase in stellar population synthesis, and this may have an impact also in the previous calibration. So we have to be careful and to revise the Magellanic Cloud cluster calibration in this around this age that is 1.75 gigayears, but it's also an age in which most of the most populous Magellanic Cloud clusters are. Okay, so this is an unfortunate, I would say, coincidence. So we have a lot of information about these clusters, not only the photometry, but also the pulsation information, but also the chemical information. So the idea is to calibrate everything together, to reproduce many constraints at the same time. So Yang Chen is analyzing now the cluster NGC 1978 and is finishing. So the paper will be soon submitted. So we were able to fulfill a number of constraints at the same time, including the chemical properties, and in terms, of course, and to predict different the calibration for the third redshift, mass loss, and also the intershell composition that needs to be oxygen enriched to reproduce this cluster. So we have to move out the Magellanic Cloud cluster. So the idea is to use a lot of galaxies, a lot of data, excellent data that we can have from, for instance, the BMC and the FAT data HST to calibrate, to have the calibration over the age metallicity plane, okay, using SMC, LMC, N31, for instance, the Milky Way badge, and also the Angst galaxies, and to couple all this photometric information with other observables, okay, long period variability, mass loss rates, chemical abundance, and so on. So the idea is to have a global calibration, not only one constraint, but many at the same time. So the calibration method is based on population synthesis technique. So from an optical color magnitude diagram, we can obtain the star formation rate, and then we can construct, using this derived star formation rate, a model for the galaxy in the near infrared where AGB stars are more prominent, and then we can start to make the comparisons, for instance, of number counts of AGB stars and to calibrate all the processes involved. Again, the tracks should be recomputed every time we change a parameter. We made this kind of exercise for Angst galaxies, so they are nearby but outside the local group galaxies surveyed with the HST. And this work was done by Philip Rosenfield, so we could probe the role of the predust mass loss in these galaxies that needed to be quite relevant for low mass, low metallicity stars. So this is just an example of the calibration, you see. So this is an example of the calibration of the mass loss, and we could put constraints on the lifetimes of low mass, low metallicity stars, and this was the final result. Few words about ongoing work with the SMC. Okay, this is a fantastic view just released by ESO yesterday from the VISTA survey. So for this galaxy, it is possible using color magnitude diagram reconstruction to obtain a specially resolved star formation history for all these subregions here. Stefano Rubile and collaborators were able to reconstruct the single specially resolved star formation history, and this is taken into account now for the calibration of the AGB phase, okay, because using this star formation history in our population synthesis code, we try to reproduce the Spitzer, the two mass actually, color magnitude diagrams towards the SMC, coupled also with the Spitzer information. So these are carbon stars in red, and these are the dusty obscured AGB stars. These are observations, okay? And JADA is taking care of that, and this is just ongoing calibration. So on the left you have the data, on the right you have population synthesis calculations made. You see, I will not bother you with the details, with different predust mass loss, dust-driven mass loss, third redshift prescriptions. And every time we check the number counts, predicted versus observed, and we find, of course, discrepancies, so we start to modify the input prescriptions. This is a bad case in which the mass loss is stripping too many stars out of the simulated diagram. We have a deficit by a factor of 3 of carbon stars. This is another example of modifying the mass loss. Okay, so we start to have more realistic numbers, but still we have an excess of low mass oxygen-rich stars, underproduction of carbon stars, and this is the final, the calibration that we have for now that should be improved further. But you see, the number starts to be comparable. So I'm just going to finish. So this is our current calibration. So we are able to reproduce the oxygen, carbon, and the extreme AGB stars within 10-20%, which is not bad, but we want, for instance, to understand this excess and other discrepancies. So this is ongoing work. Dust effects are also considered, and thanks to the revised dust formation models by Nanni, we are able now to reproduce quite well the general behavior of color diagrams at the same time, which is very important also to probe the dust properties. One final word on the fact that the same SMC simulation that you saw has been reproduced in terms of periods. So Michele Trabucchi is doing a great job together with Peter Wood and Josefina Montalban to address the pulsation properties of these stars. So this is the famous Hubble 3 PL diagram in different sequences of long period variables. And this is our one of the simulations that we can provide. So we start to be in close, we have to interpret all these features, all these sequences, and this is a work that we are doing, and hopefully it will generate very good results. So final word about the current status of the calibration. So what can we say now about the TP-AGB contribution as a function of age and metallicity? This is a map of lifetimes that correlates also with the energy, let's say, with the importance of the phase. And what we find is some kind of island of TP-AGB stars that are expected to be more prominent at solar and Magellanic clouds like metallicities, and at intermediate age around 1 or a few gigayears. You see that then there is a decrease in their importance in lifetimes at older and younger ages. Of course, this calibration needs to be refined. So I'm coming very quickly to my concluding remarks. Maybe I can leave them here, but so I hope that it has been clear that a physically sound calibration of this phase is really necessary to produce reliable galaxy models. The only way is to be very ambitious and to try to understand the physical processes that are involved. We cannot rely only on a phenomenological treatment of the phase. So the idea is to have a very good theory as much as possible, but to couple the theory with the data. A lot of fantastic data that is coming out also with the James Webb. It will be possible to improve our descriptions, and these are our targets for the moment that we want to consider. And the current calibration indicates actually that there is a favorable area in the age metallicity plane in which AGB stars are more prominent. So thank you very much for your attention. It was sorry for being too long. I realized that
it's okay.
Sorry.
So, any questions?
Thanks, Paola, for this beautiful talk. I really enjoyed. I have a question. You mentioned like 3 approaches, okay, to take care of the thermally pulsating.
Yes, in Galaxy, let's say.
Galaxy, okay.
With
So,
the idea
for
of
example, Maraston basically
yes,
follows the fuel consumption theorem. And then, of course, the synthetic approach, of, for example, of Girardi, okay? And then your approach with very detailed. How following these 3 approaches, okay, you deal with the carbon star phase, okay? So
can you repeat, how
following these 3 different approaches, you can take into account the carbon, okay? And then whether this has any impact on the, because for example, in the case of, obviously, of the fuel consumption theorem, you, I mean, this is based on the lifetimes, and if you are based on the lifetimes, you need to know also, it's based on the theory. So the fuel consumption theorem follows a certain theory, whatever it is, okay? So which is some of the criticism that Claudia Maestron received in the last years.
Yes.
So how this carbon star phase depend on the metallicity then?
Yeah, in fact, this is a very critical question. Thanks for doing it. So let me just, I was trying to, okay, these are the methods. Okay, so the third job, as you see, is a very complex process. So full stellar models can, in principle, follow it, so they can predict the formation of carbon stars, but there are big uncertainties. What is the minimum mass for a star to become carbon-rich, and so on. So the basic idea is that with stellar evolution models, and including full stellar models or my approach, or also synthetic models, you can parameterize. You have to parameterize, I think, the third job, and you change the parameters as a function of initial mass, which means age and metallicity, to reproduce, for instance, observational constraints, luminosity function of carbon stars, color distribution of carbon stars that are maybe found either via spectroscopy or by photometric selections. Okay, so the only way to constrain is to use observations varying the third job parameters, and to have a reproduction of other quantities like luminosity functions. And if you see carbon stars in a low metallicity galaxy, you will be constraining the third job in low metallicity environment. If you look at the Magellanic Cloud cluster, you are constraining the third job in intermediate metallicity ranges. In the case of the fuel consumption theorem, apparently, I think there is no real way, because it is calibrating on Magellanic Cloud clusters, and I think that the metallicity dependence is extracted from Renzini-Evoli, I think, models that go back to 1981. So they're very old stellar evolution models. So I think the idea is they want to have an empirical calibration, but in the end, I think that now we are ready to start a more challenging project, that is the one of really understanding calibrating this process, not hiding it in phenomenological descriptions. So you have to use observations of carbon stars in different metallicity environments to understand the process as a function of the metallicity. And of course, the age enters. If you have galaxies for which you have a reliable age characterization, like star formation histories given by the VMC data, for instance, we span a metallicity from 1000 in Z to 100, so it's not so small. We can try to understand the process. Also planetary nebula could be important. The post-AGB stars seems to vary single objects, but also extended service. So we have to couple, I think, all the information. So also individual studies could be very, very important. And then the statistical studies also come into, I don't know, maybe if it was enough or, thank you.
Well, I have just a short question. It changes the boosting of the AGB from the colibri to the previous isochrones?
Yes, we did, and we did
1.14 to 1.26 or something like that.
Yes, no. So in previous, in order to resolve this effect, you have to have a very fine mass spacings to construct the isochrones. And so in earlier releases of our isochrones, we didn't realize the existence of this effect, but because we had not such fine grids of stellar tracks to construct the isochrones. So once we did these very fine grids, we realized that this effect is present. By the way, we saw also a work done by Choi and Conroy, I don't know, other stellar evolution modelists that confirms that also were finding the same effect. So it is taken into account now in the simulations. There is, I think, in the web interfaces, there is also the suggestion of what should be your typical age resolution to correctly account for this effect. Of course, in statistical studies of galaxies with a lot of stars and different star formation histories, this effect may be diluted and not sometimes. Okay, sometimes okay, because we also see some, but you cannot predict a priori. Okay, but in any case, it's better to have in mind that it exists. So yeah, thank you.
Thanks for the comprehensive talk. I have a question on the physics of the third Dredge-up regarding the nucleosynthesis that you presented. It's perhaps a technical detail, but I think there may be interesting implications. So you predict, and it's well known, that the lithium can be produced through the Cameron-Fowler mechanism in that phase. So what I'm curious to know is if you have any predictions as a function of metallicity.
Yes.
Because, of course, it's well known that carbon stars show extremely high lithium abundances in some cases.
In some cases, but
already from the 60s, 80s, even I did some work in the 90s. So extremely high abundances. But the question is, have you predictions for different metallicities?
Yes.
Because is it still the Cameron-Fowler mechanism working at very low metallicities?
Okay, now, unfortunately, I don't have with me now the plots, but I remember I made some plots going from very low to higher metallicities. So I think that the lithium production, since it is linked to the electron capture on beryllium-7, and beryllium-7 comes from the helium-3, helium-4 reaction, so it is highly dependent on the temperature at the base of the convective envelope. So the higher the temperature, which usually you have, the lower the metallicity, the quicker also you destroy the beryllium that you produce. So if I remember correctly, I saw that in low metallicity, I'm thinking of hot bottom burning stars, okay, there was a spike of lithium production initially, and then a rapid destruction, because the helium-3 is rapidly destroyed, and so as soon as you don't have any more helium-3, you don't produce any more lithium. So I remember that the duration of the lithium-rich phase, if I'm correct, at very low metallicity was very, very short, and maybe unobservable. I don't know, but there was this trend. But of course, this could be very interesting to check with the models, because yeah. It's not complete answer, but we can. But we have the possibility to check this. Yes, yes. Thank you very much.
Other questions? Okay, I think we can finish here, and we have the colloquium coffee in the library for those of you that want to continue this discussion. Thank you.
Okay. Thank you very much. Sorry. Ho fatto troppo lungo, no, troppo lungo, ha fatto ritardare il colloquio di là?
No, è un colloquio caffè.